Section 1. Introduction. Throughout these videos, I've presented you with a number of equations over the rational numbers, and I've asked what its solutions are. And we've often begun by ruling out certain kinds of solutions. That's usually gone as follows. One of the first things we usually do, if necessary, is multiply through by denominators, so that we're working with integers. Then we're often able to reduce modulo m for some well-chosen integer m, and just check a few cases to show that that equation has no solutions. For example, in video 9, when trying to solve the equation 6y squared equals x times x plus 1 times x plus 2 over the integers, in other words, x plus 1, x plus 2 equals 2 times 3 times a square, we split our solution into 9 cases according to where those factors of 2 and 3 went. This looks arduous, but actually many of these cases can be ruled out immediately. Take this one as an example. These first two equations tell us that 3 alpha squared plus 1 equals 2 beta squared. And we can see quite easily that this can't have any integer solutions. If it did, it would have solutions modulo 3, and mod 3, this first term is 0. But now we can write out all the possibilities for 2 beta squared mod 3. And we can see that it's never possible for 1 to equal 2 beta squared mod 3. So there are no solutions. This is a method we've used over and over again to rule out the existence of solutions. If an equation has integer solutions, then it must have solutions mod m for every possible modulus, 2, 3, 4, 5, 6, and so on. So if we can find one case where this fails to be true, then we can conclude it has no integer solutions at all. This might lead us to ask a couple of questions. Firstly, is the converse true? That is, if we start with a rational equation, we clear its denominators and we find that it does have solutions mod m for every m at least 2, can we stitch those solutions together into a rational solution? And secondly, even if this is true, is it helpful? When might it be easier to solve all of the infinitely many equations on the right rather than just the one on the left? We'll postpone the first question for a while, and in this video we'll only address the second question. Section 2, the so-called Chinese remainder theorem. This is a useful tool in modular arithmetic. In ring-theoretic language it says the following. If m and n are coprime, then the integers modulo mn can be written as the integers modulo m times the integers modulo n. This times here is the Cartesian product of rings. But in case you're not familiar with it, I'll give a quick example as a sketch of how it works. Let's suppose we're given some unknown integer x, and I'm given that x is 1 mod 3 and 5 mod 7. Then, because 3 and 7 are coprime, this theorem tells us that I can stitch these congruences together into a single congruence mod 3 times 7, that is mod 21. Let me draw out a table with possible values of integers mod 3 down the left and possible values of integers mod 7 across the top. And let's try to fill this table in and see what happens. Let's start with the integer 0. Well, 0 is 0 mod 3 and 0 mod 7, so it goes here. Now 1, which is 1 mod 3 and 1 mod 7, so it goes here. 2 is 2 mod 3 and 2 mod 7. 3 is 0 mod 3 and 3 mod 7, so notice that this diagonal line wrapped around from bottom to top here. And let's carry on in the same way with 4, 5, 6, and then 7, which is 1 mod 3 and 0 mod 7, we wrapped around again, this time from right to left. And we can carry on filling out this whole table in the same way. Notice that we've used all the integers from 0 to 20, and 21 would end up back in this top left corner. The upshot is, encoding a value mod 3 and a value mod 7 is equivalent to encoding a value mod 21. This table is how you translate between the two. So if x is 1 mod 3 and 5 mod 7, then it must be equal to 19 mod 21. So if we know something mod 3 and mod 7, then we also know it mod 21. We don't need to calculate it again. If you've never seen this result before, you might like to draw out the same table mod 5 and mod 9 to convince yourself that it also works for prime powers. On the other hand, if you do it mod 6 and mod 9, you'll end up looping back on yourself before the whole table is complete. Try it and see if you can work out what went wrong. This is because 6 and 9 share a factor of 3. So long story short, instead of considering all possible moduli, we only need to consider the ones that are primes or powers of primes. For example, we don't need to solve anything mod 6. We already know that mod 6 can just be stitched together from working mod 2 and mod 3, so we can ignore that case. And just to make all of this easier to read, I'm going to group all of these moduli together according to the prime that they come from. So here are all the powers of 2. I'll write them like this. Here are the powers of 3, of 5, of 7, and so on. We're going to focus next on these families of congruences, one at a time. Section 3. P-adic integers. Let P be a prime number, and we're going to consider the relationships between arithmetic mod P, arithmetic mod P squared, arithmetic mod P cubed, and so on. I'll draw these out in a tower going upwards. Now, if we're given any positive integer, we can write it in base P. For example, taking P to be equal to 7 for a second, the number 125 in base 7 would be 2 times 7 squared, plus 3 times 7, plus 6. These numbers 2, 3, and 6 are the base 7 digits of the number 125. From right to left, they tell us how many 1s, 7s, and 7 squareds make up the number 125. Now, if we were to reduce this expression mod 7 squared, the 7 squared term on the left would go away, and we'd be left with just 3 times 7 plus 6. And if we reduce it further mod 7, the 7 term on the left goes away, and we're left with just 6. What if we try to go up the tower to higher powers of 7? 125 will always just be 125 mod higher powers of 7, but I'm going to leave space for the extra possible base 7 digits that might have arisen, so I'm going to put some extra zeros here. Notice, by the way, that for any positive integer written in base 7, these base 7 digits will always be between 0 and 6. As you'll have noticed, one important fact about these expansions is that they're all compatible. That is, each digit stays the same as we go up its column. The right-hand digit will always be 6 no matter how high up we go. The next along will always be 3, and so on. Now let's go back to the general case of base P. We can write any positive integer like this. Just like in base 10 we write numbers using units, tens, hundreds, thousands, and so on. Given any positive integer, we can first reduce it mod P to find out its units digit. Then we can reduce it mod P squared to find out its P's digit. Then mod P cubed to find out its P squareds digit, and so on. And of course, all of these digits are going to be between 0 and P minus 1. So let me introduce some shorthand. I'm going to write the number represented by this whole tower of information by just the sequence of coefficients inside square brackets, with a little p at the end to show that we're working base P. I've written some dots at the left to show that we're including the whole infinite sequence of coefficients, even if almost all of them are 0. So for example, we saw before that 125 can be written in base 7 as 2 times 7 squared, plus 3 times 7, plus 6. Each digit here represents a multiple of a power of 7. And all the other coefficients to the left were just 0. Here's another example. The number 500 written in base 11 is 4 times 11 squared plus 1 times 11 plus 5. Now you might ask why I'm bothering to write all the zeros at the front. After all, in base 10 we don't usually write them. And that's partly because I'm going to expand this number system in a minute. But it's also partly because the restriction I wrote in the lower right, that all coefficients have to be between 0 and p minus 1, has a couple of interesting consequences. So let's play around with this restriction for a minute. What happens if I try to write minus 1 in base 5, using the method I outlined earlier and only using digits between 0 and 4? Well, mod 5, the number minus 1 is just equal to 4. Mod 5 squared, it's 24, which is 4 5s plus 4. Mod 5 cubed, it's 124, which is 4 5 squareds plus 4 5s plus 4, and so on. If minus 1 has a representation in this system, it has to go off towards the left as an infinite string of 4s. In fact, this number system can represent more than just integers. You might remember that we talked about division in modular arithmetic early on in video 10, and if so, you might like to try to convince yourself that a half can be written in base 5 as an infinite repeating string of 2s followed by a 3 at the end. Let me get a little bit ahead of myself here. Given a prime p, I'm going to define the set of p-adic integers, which I'll denote z subscript p, to be the set of sequences of base p digits like this. If you like, you can think of them as infinite sums going off to the left. I'm going to insist that all of these digits should be between 0 and p minus 1, but notice that otherwise I'm not putting any restriction on them. They don't have to eventually become 0 or eventually repeat or anything like that. Each element of ZP encodes a whole tower of compatible numbers modulo powers of p, and vice versa. So given a tower like this, you might like to think of the element of ZP as sitting on top of the tower equivalent to all the information below it. And so rather than talking about solving an equation mod p to the n for all n, we're just going to talk about solving an equation inside ZP. Right? These are the same thing. Now there's a lot more to say about these things, and I do hope to come back to them later, but for now we'll content ourselves with the following properties. Firstly, ZP is not just a set, it's actually a ring. That is, we can add, subtract, and multiply its elements. In fact, the method is almost exactly the way you learn to add, subtract, and multiply in primary school, but now accounting for the infinitely many digits to the left. For example, in the 7 adic integers, we can write 18 as 2 7s plus 4 1s, and 54 as 1 7 squared plus no 7s plus 5 1s. And to add these, we just write out their digits in columns, aligned at the right, and we add down the columns from right to left. So starting at the right, 4 plus 5 is 9, but we're going to write 9 in base 7. That is, it's 1 7 plus 2 1s, which we can write 7-adically like this. And so we're going to mark this 2 here, and we carry the 1 to the left. Okay, in the next column over, 2 plus 0, plus that 1 we just carried over is 3. In the next column, 0 plus 1 is 1. And all the rest are just going to be zeros. So we get this number here, 1 7 squared, plus 3 7s, plus 2 1s, which is in fact 72, as we'd have hoped. Multiplication in this system is also exactly what you'd expect, and subtraction is what you'd expect after taking into account the strange representation of negative numbers in this context, as we saw an example of earlier. Secondly, we've seen that we can write all positive integers as p-adic integers, and I gave an example of how to write minus 1 as a p-adic integer when p equaled 5 earlier. In fact, all integers can be written as p-adic integers for all primes p, so I'm going to regard z as a subring of zp. But the two aren't equal, as evidenced by the fact that z5 contains the element a half. In fact, zp is much larger than z, as we'll see shortly. Thirdly, our p-adic valuation function, vp, that counts the number of factors of p in the number, makes sense not just for integers, but for p-adic integers as well. For example, let me write out a 7-adic integer at random. Remember that the rightmost is the 1's digit, then the 7's digit, the 7 squared's digit, the 7 cubed's digit, and so on. The first non-zero digit here is in the 7 cubed's column, which means that 7 divides this number exactly 3 times. So the 7-adic valuation here is 3. Notice that every p-adic integer has a p-valuation that's an integer, which is at least 0, and the only thing that has infinite p-valuation is the number 0 written as a p-adic integer, which is a string of all zeros. There's an important conceptual shift to be made about size and distance, though. The p-adic numbers aren't designed to measure these in the usual sense. The further to the left a digit is, the smaller and less significant we should regard it as being. So numbers with large p-valuation, that is, lots of factors of p, so more and more zeros on the right in this representation, are meant to be interpreted as close to zero somehow. And this leads to the following way of picturing the p-adic integers. It's not necessarily the most useful diagram, but it does show how different the p-adic integers can be from the usual integers. For concreteness, I'll take p equals 5, so I'm going to draw you a diagram of all the 5-adic integers. They're going to lie inside this circle here. I'll write a generic 5-adic integer as before, with 5-adic digits a0, a1, a2, and so on. And firstly, I'll arrange them according to their most significant digit, a0. Now there are 5 possibilities for a0. It can be 0, 1, 2, 3, or 4. Every 5-adic integer lives in one of these 5 circles. And of course, if we reduce this number mod 5, we chop off everything apart from this final digit, so this rightmost digit tells us whether our number is 0, 1, 2, 3, or 4, mod 5. Next, I'll split up each of these circles and arrange elements according to their next most significant digit, a1. So for example, if a0 happened to be equal to 2, our number would lie inside one of these smaller circles according to whether its a1 digit is 0, 1, 2, 3, or 4. And the same is true for all the other possible values of a0. And if you like, each one of these small circles tells us what our number is mod 25. That is, we've chopped off all but the last 2 digits. And I can keep going. Mod 5 cubed, mod 5 to the 4, and so on. And if I repeat this process forever, each point that these circles converge on represents a 5-adic integer. Now, in this picture, 2 numbers are 5-adically close to each other if the nearest circle they share is small. For example, consider 2 numbers here on the diagram. The smallest circle they share is this one, which is 3 layers deep. So these numbers have the same a0 digit, the same a1 digit, and the same a2 digit, but not the same a3 digit. This puts them quite close together. On the other hand, these numbers differ at the a2 digit, which means that they're a step further apart. And these numbers differ at the a1 digit, so they're a step further apart again. At this stage, we have a few unanswered questions about the p-adic integers. For example, how are we supposed to think about them? Which numbers, other than the usual integers, can be written as p-adic integers? And what are they useful for? Section 4. P-adic functions. Before we consider number theoretic problems over ZP, we need to say a few words about functions from ZP to ZP in the abstract. Everything we've considered so far has been a polynomial, and we're going to continue only considering polynomials. There are other functions, but this will make our life a little easier because polynomials don't require any special extra definitions. For example, 3x squared minus 2x plus 5 is just shorthand for 3 times x minus 2 times x plus 5. That is, in order to write down a polynomial, all we need to use is addition, subtraction, and multiplication. And since this is all we need, and I've already told you that all of these things exist on ZP, there are no extra difficulties involved in defining polynomials. But since we have an unfamiliar notion of distance in this context, anything that involves limits or convergence needs to be double-checked. So let's define what we mean by a derivative of a polynomial in the p-adic context. As a spoiler, nothing unexpected actually comes out of this, but it is healthy to check. Now, intuitively, we want to say that the derivative of a function f at a point A is the best linear approximation to f at A. That is, if we're sitting at the point a, f of A on the curve, and we move a very small distance left or right along the curve, it should feel as though we're more or less moving up or down along the tangent line of slope f prime of A. As we get further from this starting point, This approximation might get worse, but at least for very small distances, the curve and the line are roughly the same. So to write this out formally, if h is small, we should have that f of a plus h is approximately equal to f of a plus the linear term f prime of a times h. That's the slope times how far you've gone left or right. More precisely, when I say approximately equal to here, what I mean is that the error term should be at least quadratic in h, so that if h is small, it disappears very quickly. We can calculate this for polynomials easily. For example, if f of x is x cubed, then we can calculate f of x plus h. That's just x plus h cubed, which we can expand out as x cubed plus 3x squared h plus 3xh squared plus h cubed. That's x cubed plus a linear term plus some quadratic and higher terms. So by comparing the linear terms in these two equations, we can read off the fact that f prime of x, the derivative of f at x, is 3x squared. Okay? In fact, exactly as we'd expect for polynomials in the usual context, if f of x is x to the n, then its derivative is nx to the n minus 1. You can check this using the binomial theorem. Now, in the p-adic context, the derivative no longer represents slope or gradient in the same way. P-adic functions are hard to draw because our numbers don't really meaningfully lie along a line anymore. But we can still calculate the derivative of a polynomial exactly as for real functions, and we're going to use that crucially in the following section. Section 5. Approximate roots of functions. Let's go back to an analogy with real functions. Consider the following procedure. We'll start with this curve, y equals f of x. At this point, the curve is above the x-axis, and at this point, the curve is below the x-axis. So, there must be a root somewhere in between these 2 points. I'm going to just focus on that point on the right, and I'll call it r0. It's not a root of our function, but it is close to a root. It's approximately a root. Now, if I draw the tangent line to our curve at this point, and I look at where that tangent line intersects the x-axis, say r1, well, this also isn't the root, but it's much closer to the root. And we can zoom in and repeat the procedure. Find the point on the curve corresponding to r1, draw the tangent line through it, see where it cuts the x-axis, and call that point r2. This is now much closer again. And we can zoom in again, find the point on the curve corresponding to r2, and so on. In other words, given a nice enough real function, y equals f of x, and a good enough approximate root Rn, so that f of Rn is close to 0, we draw the tangent line through the corresponding point on the curve. That's Rn, f of Rn, and that's going to have gradient f prime of Rn by definition. And then we find where it intersects the x-axis, and we call that point Rn plus 1. If you do that calculation, you'll see that you're setting Rn plus 1 equal to Rn minus f of Rn over f prime of Rn. Keep that formula in mind, because it'll come up again in a minute. The point is, under appropriate conditions, this will converge to a root, x equals r, and this is called the Newton-Raphson method when it's applied to real functions. Okay, with that in mind, let's change gears. Suppose f is a polynomial on the p-adic integers, and suppose we have some p-adic integer Rn such that f of Rn is very close to 0. Say, it's equal to 0 mod p to the n. In other words, if we write out all the digits of Rn as a0, a1, and so on, then we apply f. The last n digits in the p-adic representation of this result are all zeros. Now, this whole calculation is happening mod p to the n at this stage, so these digits on the left aren't going to have any effect on the end result, and these digits on the right might be non-zero. Okay, what if we decide to try to take the digit an into account? Well, then we'll get some digit in position n on the right, let's call that digit c, but c might not be 0, because Rn is only an approximate root. It's accurate to at least n digits, but maybe not to n+1 digits. So, can we get a better root? Can we modify this digit an to get a solution that's even more accurate, say accurate to at least n+1 digits? In other words, we want the following. If I write this expression out again, but I modify the nth digit, say by adding an integer h to it, then I want to get an extra 0 on the right. How can I do that? Well, let's try it. We're going to take Rn, and we're going to add on h in the nth digit. So we learned earlier that if we do this, we take Rn plus p to the nh, and then we apply f to it. Then we get f of Rn plus some linear error term, plus some quadratic and higher error terms. Okay, this linear error term is the derivative, f prime of Rn, times p to the nh. And the rest, a multiple of p to the nh all squared, is going to be 0 mod p to the n+1 anyway, so I don't really care about that at this stage. Mod p to the n+1, these two expressions are equal. And what we want is to pick a value of h such that this right-hand side is 0 mod p to the n+1. So if we can choose an integer h such that h is minus f of Rn over p to the n f prime of Rn mod p, we do get 0. Let me tidy this up a bit. What I'm really saying here is, if I set Rn+1 equal to Rn plus p to the nh, that is Rn minus f of Rn over f prime of Rn, the formula from before, we get f of Rn+1 equals 0 mod p to the n+1. Now, I emphasized that this was true as long as we can choose such an integer h. Why might we not be able to? The problem is that ZP has addition, subtraction, and multiplication, but not always division. In particular, everything in ZP has p-valuation at least 0. So if there are too many factors of p in the denominator, this won't make sense. Or I could put this another way. We're not allowed to divide by p in arithmetic modulo p. So that factor of p to the n on the bottom looks a little worrying, but it's okay because there are at least n factors of p on the top, and there are n factors of p here, so they'll all cancel out. But a problem will arise if there are any more factors of p hiding in f prime of Rn. So, in order to ensure that we can choose an integer h like this, let's just insist that the p-valuation of f prime of Rn is 0. In other words, f prime of Rn is non-zero mod p. Moreover, this means that the p-valuation of this term here is at least n. So if we reduce mod p to the n, Rn and Rn+1 are equal. Okay, so if f prime of Rn is non-zero mod p, then f prime of Rn+1 must be non-zero mod p. So here's what we have. If we have some Rn in Zp, which is an approximate root to f, accurate to n digits, and the derivative of f at that point is non-zero mod p, then our iterative formula from earlier gives us an Rn+1 in Zp, which is an approximate root to f, now accurate to n+1 digits, and the derivative at Rn+1 is also non-zero mod p. If I take Rn+1 and I reduce it mod p to the n, I get back to where I started. Here's how you should think of this. This iterative formula takes us from a good approximation to a better approximation. So if we start with a good enough approximation R1, so f of R1 is 0 mod p, and f prime of R1 is non-zero mod p, then we can lift it to a better approximation, R2 mod p squared. And we can then lift that to R3 mod p cubed, and R4 mod p to the 4, and so on forever. We can keep lifting an approximate root to a slightly better root. The p-adic number we get in this way will then be a genuine root of f. This is called Hensel's lemma, and in my opinion it's the most important fact about the p-adic integers, so I'm going to really labour the point and state it one more time. If f of x has a simple root, R1 mod p, that is, f is 0 mod p there, but f prime is non-zero mod p there, then f of x has a root in zp, and we can construct it by this lifting procedure. Earlier we asked which numbers are p-adic integers, and in practice Hensel's lemma is going to be really useful for working this out. If f of x has no roots mod p, then of course it has no roots in zp. And Hensel's lemma tells us a partial converse to this, which is that if f of x has a simple root mod p, then it has a simple root in zp. There is also a third case here, when f of x has a multiple root mod p, but for now we'll just say that we don't have enough information to draw a conclusion. Here's an example of how to put this into practice. I'm going to show that z5 contains an I, that is, a square root of -1, but also that z3 doesn't. Let f of x be x squared plus 1. This is the minimal polynomial that we'd expect I to satisfy. Okay, then the derivative of f is 2x, and f has a simple root mod 5, for example x equals 2. Let's check that. That's because f of 2, which is 2 squared plus 1, is 0 mod 5, but f prime of 2, which is 2 times 2, is non-zero mod 5. So, Hensel's lemma tells us immediately that f has a root in z5. That is, there is some number I in z5 such that I squared equals -1. Notice that we don't have to go to the trouble of actually constructing this number in order to know that it exists. On the other hand, f has no roots at all mod 3. There are only 3 cases to check, 0, 1 and 2, and when you apply f to all of these you never get 0. So f can't have a root in z3, because if it did we could just reduce it mod 3 to get a root mod 3. Here are some exercises. Firstly, show that z7 has a square root of 2, but z11 doesn't. Secondly, show that zp contains the rational number a over b, where a and b are integers, whenever b is co-prime to p. And thirdly, show that z5 has a square root of 6, but z3 doesn't. Those first 2 questions can be done in the same way as the example on the previous slide, just write down an appropriate polynomial. For the third, here's a hint. If a square root of 6 existed in z3, what would its three-adic valuation be? Finally, as a bit of an off-topic exercise, you can also show that not all elements of zp satisfy a polynomial with coefficients in z. That is, some elements are transcendental over the integers. This implies that zp is much larger than z, and in fact much larger than most of the rings we've worked with so far in this series. But for now we're not going to need that fact. So, armed with this knowledge, let's prove a small lemma. Suppose that p is odd, r is a p-adic integer, and r is non-zero mod p. Then r is a square, if and only if it's a square mod p. Okay, so to check whether r is a square, we only need to look at its last digit. Alright, one direction of the proof is easy. If we've got something in zp, we can always just reduce it mod p. So if r is the square of something inside zp, say it's s squared, then the same will be true when we reduce this equation mod p. So let's look at the other direction. Suppose that s squared equals r mod p. Then the polynomial f of x equals x squared minus r has a root mod p, namely x equals s. Okay. And if s was 0 mod p, then r would be 0 mod p, which isn't allowed, so s must be non-zero mod p. Now, the derivative of f is 2x, and since p is odd, f prime of s, which is 2 times s, is non-zero mod p. And that's it. We've shown that f has a simple root mod p, so now Hensel's lemma tells us that we can lift s to a genuine root of f inside zp, and we're done. So under these conditions, the p-adic integer r is a square if and only if r over p, that's the Legendre symbol we defined back in video 11, which tells us whether or not r is a square mod p, is equal to 1. Section 6. Sums of 3 squares. In upcoming videos, we'll explore the following question. When can a positive integer n be written as the sum of squares of three integers? That is, x squared plus y squared plus z squared equals n, where x, y, and z are in z. This video will show that the corresponding question over zp is much easier to answer. Let's consider two questions. Question 1. When can a positive integer n be written as the sum of three p-adic squares, that is, x squared plus y squared plus z squared equals n, where x, y, and z are in zp? And when p is odd, we'll consider the very closely related question 2. When can 0 be written as the sum 1 plus b squared plus c squared, where b and c are in zp? Okay, so when p is odd, what's the relationship between these two questions? Well, suppose we have numbers b and c as in question 2. Suppose we have p-adic integers b and c such that 1 plus b squared plus c squared equals 0. We'll apply a little change of variables trick. We'll set x equals 1 plus n over 4, y equals b times 1 minus n over 4, and z equals c times 1 minus n over 4. Remember here that even though you can't always divide inside zp, if p is odd, then 1 over 4 is an element of zp by one of the exercises from earlier in this video. So this makes sense. Then you can multiply them out to c. X squared plus y squared plus z squared does equal n. So if we have a solution to question 2 for an odd prime p, this trick gives us a solution to question 1. So let's solve question 2 for odd primes p. Well, firstly, if zp contains an I, then setting b equals I and c equals 0 is the solution. 1 plus I squared equals 0. Secondly, actually just a slight generalization of the above fact, if zp contains both the square root of some number a and the square root of minus a plus 1, then setting these equal to b and c respectively is also a solution. So let's assume that neither is true. So suppose we've got some fixed prime number p, and consider what kinds of elements zp has. We'll assume that minus 1 is not a square in zp. So by our earlier lemma, the Legendre symbol minus 1 over p equals minus 1. And we'll assume that if the number a is a square in zp, then minus a plus 1 is not a square mod p. So if a over p is plus 1, then minus a plus 1 over p will be minus 1. Now remember that the Legendre symbol is multiplicative on the top. So if I multiply these two together, I get that a plus 1 over p equals plus 1. Okay, so for this prime p, we've proved that whenever a over p equals 1, we also have a plus 1 over p equals 1. In particular, 1 over p equals 1, because 1 is a square mod p. And therefore, 2 over p equals 1. And so 3 over p equals 1, all the way up to p minus 1 over p equals 1. But this is the same thing as minus 1 over p, which we assumed equal to minus 1. So this contradicts our assumption. Every zp must either contain an I, or must contain the square root of a and the square root of minus a plus 1 for some number a. Okay, so we've answered question 2 for all odd p, and therefore we've answered question 1 for all odd p. Every positive integer n can be written as a sum of 3 p-adic squares for every odd p. The 2-adic case is a little trickier, so let's go back to our question in this case. When can a positive integer n be written as a sum of 3 2-adic squares? Well, let's start off with a lemma. Suppose n is 1 mod 8. Then I claim there exists a in Z2 such that a squared equals n. Notice that this is a very special case of our question. It tells us that whenever n is 1 mod 8, we can take x to be this a and just set y and z to be 0. The proof goes as follows. Ideally, we'd like to apply Hensel's lemma to f of x equals x squared minus n. F does have a root mod 2, For example, f of 1 is 0 mod 2, it's even 0 mod 8. But this isn't a simple root, because the derivative f prime of 1 is also 0 mod 2. So we can't apply Hensel's lemma directly. But let's try to adapt the proof anyway. I'm going to take this number 1, and I'm going to modify the next digit along, that's the 2's digit, by an integer h. So f of 1 plus 2h, that's 1 plus 2h squared minus n. Expanding that out, that's 1 minus n plus 4h squared. And 1 minus n is just f of 1. So we can rewrite this as f of 1 plus 4h squared. But something interesting happens here. F of 1 is 0 mod 8, so it's divisible by 8. Which means that all three of these terms have a factor of 4 in common. Well, let's divide out by it. We'll set g of x equals f of 1 over 4 plus x squared. This is still a p-adic polynomial, and we've chosen it specifically so that f of 1 plus 2h is 4 times g of h. In particular, if g has a root, then f has a root. But now, g of 0 is 0 mod 2, so g has a root at h equals 0, corresponding to the root of f that occurred at x equals 1. And importantly, the derivative of g is non-zero mod 2 at h equals 0. So we can apply Hensel's lemma to g to find a root. Okay, let's return to our main question and consider all of the possibilities mod 8. Firstly, mod 8, x could be anything between 0 and 7. If we square all of those, we see that the only possibilities for x squared are 0, 1, or 4 mod 8. And similarly, the only possibilities for y squared and z squared are 0, 1, or 4 mod 8. So let's write out a table of all the possibilities for x squared, y squared, and z squared, ignoring potential rearrangements. Well, they could all be 0 mod 8, or there could be 2 zeros, in which case the remaining one could be either 1 or 4, or there could be 1 0, in which case these are the possibilities, or there could be no zeros, in which case these are the possibilities. So here are all the possibilities for x squared, y squared, and z squared, and now let's add them up to work out what possibilities they give us for n mod 8. And here's our first interesting restriction. By considering everything mod 8, we've shown that n can take any value between 0 and 6 mod 8. That is, n cannot be 7 mod 8. If n is 7 mod 8, there are no x, y, and z in Z2, such that x squared plus y squared plus z squared equals n. Okay. What about in the other cases? Well, let's impose a series of simplifications. Firstly, if n is divisible by 4, in other words, it's 0 or 4 mod 8, then it lies in one of these columns. And notice that in all of these cases, x, y, and z are all even. So dividing the whole equation by 4 gives us x over 2 squared plus y over 2 squared plus z over 2 squared equals n over 4. And this is another p-adic equation of the same type with an integer on the right. It's just got one fewer factor of 4 throughout than the previous equation. So we can repeat this as many times as necessary to eventually get rid of all of the factors of 4 dividing n, so that we're left with an n that is 1, 2, 3, 5, or 6 mod 8. Secondly, all of these remaining columns have a 1 in them, and in all of these cases it will be helpful to relabel our variables so that x squared equals 1 mod 8. So let me just swap these numbers around. Thirdly, notice that if n equals 1 mod 8, there are two types of solutions that were allowed. Solutions where both y squared and z squared are 0 mod 8, and solutions where they're both 4 mod 8. Now, I'm going to make life harder for us and only allow us to find solutions where both y squared and z squared are 0. So I'm going to erase this last column. And fourthly, remember that y and z are allowed to be any p-adic integers whose squares are 0, 1, or 4 mod 8. That gives us infinitely many possibilities. But again, I'm going to make life much harder for us, and I'm going to only allow 3 possibilities. I'm going to insist that y and z are allowed to be equal to the integers 0, 1, or 2. Note, not 0, 1 or 2 mod 8, but 0, 1 or 2 exactly. With all these simplifications in mind, we're trying to solve the equation x squared equals n minus y squared minus z squared. And depending on the value of n mod 8, we've already fixed the values of y and z. But this right-hand side is still a positive integer, and it's equal to 1 mod 8. And we've already seen that a solution does exist in this case with our earlier lemma. So finally, here's our conclusion. If n is a positive integer, then x squared plus y squared plus z squared equals n has solutions in Zp for all primes p. That is, n is the sum of 3 p-adic squares for all primes p, if and only if n is not a bunch of 4s times something that is 7 mod 8. Back at the beginning, we discussed the idea of taking an equation over z and splitting it into infinitely many equations, 1 modulo every prime power, and we asked, is it ever going to be easy to solve all of those infinitely many equations? Well, hopefully this example shows that, at least when armed with Hensel's lemma, that can sometimes be very easy. In this case, almost all of the primes, in fact all primes apart from 2, had no effect on the end result, and the only restriction came from looking modulo 8, which is a single small power of 2. But of course, our original question was over z. Can we somehow use this p-adic information to retrieve information about our question over z? We'll discuss that in the next video.